Hey guys, welcome to video 70. We're going to continue our analysis of the preamp sections of some amplifiers that are out there in the world. And today we're going to look at the Vox AC2/30. This is a 30 watt amplifier that was produced in the late 50s, and it's been superseded by other Vox models, but I thought it might be interesting to take a look at this one. We're also going to see what happens if we swap out this tube for a different one, and let's start by taking a look at the overall operation of this circuit. Just like the Marshall amplifier we looked at in the previous video, this has a high gain input section and a low gain input section. There are no input coupling capacitors used, and if we choose the high gain inputs, our signal is going to go through both stages of amplification. If we choose the low gain input, we're going to bypass the first stage and just use the second stage. Now, this amplifier was designed around the 12AU7, and notice that both stages have the same plate and cathode resistor values, so they're going to have the same Q points and the same DC load lines. The first stage is a common cathode with full cathode bypassing, so it'll be the relatively high voltage gain section. And the second stage is the common cathode with no cathode bypassing, so this is going to be a relatively low voltage gain stage. Now, let's come on over and assume we're using one of the high gain inputs. Our guitar is going to see about 400 k ohms looking into the input jack, and we know we're going to get a larger signal here at the plate, which is coupled through C1 over to R8, which is the volume control, and I'm going to have more to say about this in a minute. But coming on over here, we've got R9 and C4. This forms a treble cut circuit. If the wiper is set all the way to the top of R9, we've got this 0.005 microfarad cap connected from this node to ground, and that cuts some of the treble. If the wiper is all the way down here at the bottom, we're not going to have much treble cut. And over here, we're going to see a variable resistance. If the wiper is all the way down at the bottom, we have the low gain section turned down to 0. We're going to see 1 megohm. If the wiper is all the way up top, we're going to see 1 megohm in parallel with 110K. So what it boils down to is, as we adjust these potentiometers, we're going to be changing the AC load on stage 1, which means its AC load line can vary pretty drastically. So we're going to have to think about this a little bit when we do our analysis. But in any case, moving on here to the second stage, again, we don't have a bypass on the cathode, so the gain of this stage is going to be relatively low, and the output is taken across R13 and fed into the next section of the amplifier. Okay, now before we go plotting load lines and calculating Q points and stuff, I want to come over here and look at R8 for a second. Let's assume we're using the high gain input and we've got it set for maximum volume, so the wiper is all the way up the top of the pot here. We'll set the tone control for minimal effect, so its wiper is down at the bottom, and since we're not using the low gain input, we'll set R10 down to the bottom of its travel as well. So now what we're looking at out of the plate of this tube is 1 meg in parallel with 1 meg in parallel with 1 meg. So we're going to see about 333 k ohms for our large signal AC plate resistance. Now, as we turn this pot down to decrease our output volume, notice that the effective load resistance we're driving is going to get smaller and smaller, and when that happens, the AC load line for this first stage gets steeper and steeper. I don't like to design amplifiers that do this, that change the AC load line when you adjust the volume, so although I'm not the be-all and end-all of amplifier designers or anything, this is probably not how I would approach this, but hey, who am I to criticize Vox? So anyway, when we have this thing turned all the way down to 0 volume, we're shorting the output to ground, so effectively the AC load line for the first stage is vertical. I don't like to design amps that way, but that's what we've got here. Okay, so with the overview out of the way, let's just go ahead and find our DC load lines. And remember, since both stages are the same from a DC perspective, we only need to find one DC load line. All right, our first value is VPK cutoff, and that's just equal to VPP, which is 210 volts. IP sat is equal to VPP over RP plus RK. And since RP is 100K and RK is only 1.5K, we can just disregard RK here. And we get 210 volts divided by 100K, which is 2.1 milliamps. Now you can see at this low current value we're just using the very small corner of the plate curves, and unfortunately that doesn't give us very high resolution for our work here, but we'll do the best we can. So here's our DC load line extending from 2.1 milliamps to 210 volts. Now what we need to do next is plot our bias line and find the intersection of that line with our load line to get our Q point. So remember, we're working with the equation I sub P equals V sub GK divided by R sub K, and well, there is a negative sign here, but what we're going to do is pick a convenient value of VGK, find the resulting I sub P value, and plot that line given 2 points. So the first point I use is VGK of 0 volts, which produces 0 plate current, so that gives us a point here at the origin. And let's try using the 12 volt grid to cathode curve here. So VGK is negative 12 volts. I sub P is going to be 12 divided by RK, which is 1.5K. And that gives us 8 milliamps. And the coordinates of this point are right here. So let me change colors and draw our bias line in, and this is what we've got. So I'm going to change colors to purple, which I've been using for my Q points so far, and this is what we have. And again, going back to blue, it looks like we've got a VPK of about 60 volts, and our current is that's pretty close to 1.5 milliamps, so things line up pretty well with the published values and the current that I calculated based on those values. Now, what I'd like to do next is determine the large and small signal AC resistance values for the circuit. So let me clear off my work here to open up this space. And let's start by looking at the plate resistance we'd see coming out of the first stage. So we're going to see an R prime L, that is an effective AC load resistance of R6 in parallel with, let's say we're going to set it for maximum volume, so we're going to see 1 meg here for R8 and R9, and finally R10. So we're going to see all of these resistors in parallel. So that's 100K in parallel with 1 meg, 1 meg, 1 meg. That's 333K. And that works out to be about 77 k ohms. So RL for the first stage, let me throw a 1 here, is about 77 k ohms. Now our external cathode resistance R prime K for the AC large signal analysis or small signal is 0 because we're fully bypassing. So that's 0 ohms. And now coming over to the second stage, let's see, its plate resistance, or actually load resistance, R prime L for stage 2 is going to be R11 in parallel with R13. So that's 100K. in parallel with 1 megohm, and that works out to be about 91 k ohms. And since we're not bypassing the cathode, R prime K for stage 2 is equal to 1.5 k ohms. And let me throw a sub 1 over here on this R prime K. All right, now the next thing I'm going to do is determine the voltage gain for each stage, and we're going to be using these values for mu, GM, and little rp. And I got these from the data sheet using the characteristic curves. Let me pull that up for a second. Based on our plate to cathode voltage and our plate current, I was working over here. So I used these curves to determine all the small signal parameters. And so if they look a little odd to you, R sub P is a little bit on the high side, GM is a little bit on the low side. That's why, because I used the parameters from the datasheet characteristic curves. Okay, let's start by finding the small signal plate resistances. So that'll be R prime P1, which is R prime L1 in parallel with little rp. So that's 77K in parallel with 13K. And that works out to be 11.1 k ohms. All right, RP, R prime P2 is R prime L2 in parallel with little rp. And this time we've got 91K in parallel with 13K. And that gives us 11.4 k ohms. So not too much difference between these two. And we're a little bit low on space, so let me clear out some of this work here, and we'll determine the voltage gain next. Okay, so there we go. That looks pretty good. All right, so the gain for the first stage, and let me get my pencil back here, AV1 is equal to negative GM times R prime P1. So we've got negative 1.3 millimos times 11.1 k ohms, and that works out to be about negative 14.4. All right, now for the second stage, because we're not using bypassing, we've got to use the more complicated formula. So AV2 is going to equal negative GM times R prime P2 divided by 1 plus GM times R prime K for stage 2. And that works out to be in the numerator negative 14.8 divided by 3. So the gain for the second stage then works out to be about negative 5. Okay, and that makes sense. This is the low gain stage, gain negative 5. First stage has a gain of about negative 14.4. Now, as usual, I'm not going to leave you with these nearly indecipherable hieroglyphics. I did condense all of this into one neat page, and this is going to be much easier to study to see what's going on. And I'll leave this here for a second so you can take a look at it. And then we're going to talk about the AC load lines. And let's remember these R prime L values for the AC load line analysis. 77K for stage 1 and 91K for stage 2. And let's come on over and get to work on this. For stage 1, we're going to start by remembering R prime L for stage 1 was 77 k ohms, and R prime L for stage 2 was equal to 91 k ohms. That way I won't forget these. All right, now we're going to start by finding the AC load line saturation current, which is IP sat, and that's IPQ plus VPK Q divided by R prime L. So it's 1.5 milliamps plus 60 volts divided by 77 k ohms, and that's 1.5 milliamps plus 0.78 milliamps. So our plate saturation current is 2.3 milliamps. Now, VPK cutoff for the first stage is VPK Q plus IPQ times R prime L1. All right, so we've got 60 volts plus 1.5 milliamps times 77 k ohms. So it's 60 volts plus 116 volts, and that's 176 volts. So there are the endpoints for our AC load line on stage 1, and let's plot those. So I changed the pen color to red, and our AC saturation current is not going to be a heck of a lot different than the DC IP sat. We've got 2.1 milliamps versus 2.3, so the difference here is negligible, but connecting the two endpoints over here is 176 volts. There's our AC load line. Not a heck of a lot different than DC load line, but it was a good exercise to determine it anyway. All right, so now let's go on over to the second stage, and IP sat over here is equal to, again, IPQ plus VPKQ, except this time we're dividing by R prime L2 plus R prime K2 because we don't have a bypass cap on the cathode here. So we've got 1.5 milliamps plus 60 volts over, what was 91 K plus 1.5 K, and we have 1.5 milliamps plus 60 volts divided by 92.5 k ohms for 1.5 milliamps plus about 0.65 milliamps, which works out to be 2.15 milliamps, and that's really so close to the DC saturation current that we wouldn't be able to see the difference on this graph. But let's just go ahead and find our VPK cutoff, and we've got VPK cutoff is VPK Q plus IPQ times R prime L2 plus R prime K2. A little bit close for space here. 60 volts plus 1.5 milliamps times 92.5 k ohms, and that works out to be 60 volts plus 139 volts, which is 199 volts. So the load line for stage 2, the AC load line, is going to be even closer to the DC load line than for the first stage. So let's just go ahead and plot it, see what it looks like. And here we are. There is our AC load line, and it's almost indistinguishable from the DC load line. And now, of course, I'm not going to leave you with this mess. I'm going to give you a nicer version of this, so let's scroll on over and take a look at that. And here we go. And because in the second case the AC load line was right on top of the DC load line, I used a dashed line, and hopefully this is all decipherable. Now let's go on back over to the original schematic here, and remember we're using a 12AU7 in this circuit, and that's a pretty low gain tube. And one thing that people like to do sometimes is swap out tubes to get higher gain. And this is a perfect example of an amplifier where you might want to do that. We could say substitute a 12AX7 in place of the 12AU7 and really crank the gain up here. But I don't like to just arbitrarily swap tubes. I like to know what's going to happen before I do that. Normally it's not a problem, but you never know. So let's say that we wanted to increase the gain, so we're going to put a 12AX7 in here. Let's do a little bit of analysis of this circuit to see what would happen if we did that. So let's come on down to the next page and we'll address this question. So here's the circuit with the 12AX7 substituted in for the 12AU7, and let's start just by looking at the DC load line. Again, we haven't changed the plate or cathode resistors on either stage, so the endpoints of the DC load line are going to be the same. That is, VPK cutoff is still 210 volts, and IP sat is still approximately 210 volts divided by 100K, or 2.1 milliamps. So let's sketch in our DC load line, and here it is. And next we're going to do our bias line to determine where our Q point is going to be. And because the 12AU7 and 12AX7 have such drastically different parameters, the Q point is going to be affected pretty significantly as well. So let's set up our little table with VGK and I sub P. And again, choosing the easy point right at the origin. Let's go with VGK equals negative 1.5 volts, this curve right here. That's convenient because that results in a plate current of 1.5 volts divided by 1.5K, which is 1 milliamp. So negative 1.5 volts, 1 milliamp. Let's locate that point. Here's 1 milliamp coming out to the 1.5 volt curve. Here's the second point for our bias line, and let's draw that in using green again. And here we go. And the intersection of the bias line and the DC load line looks like we've got, well, about 0.75 milliamps for plate current, and this looks like about 135 volts for VPKQ. Now, this Q point location is significantly different from the original version. If you remember, the Q point for the 12AU7 version was giving us a VPKQ of about 60 volts. So we've moved over quite a bit, but it looks like a decent location though in terms of signal swing, so everything looks good so far. Now the next thing I want to do is calculate some of our AC resistance values for small signal and large signal analysis. So let me clear out this work for our bias line. We'll switch back to blue. And let's determine our external AC load resistors for both stages. Remember, that's not going to change, but I'm going to approximate the R'(L) values for both stages to be approximately 100K in parallel with 1 meg. That's going to be close enough. There wasn't that much of a difference between them. So we've got 100K in parallel with 1 meg. And that works out to be about 91 k ohms. Our R'(P) values for both stages are going to be the same then, and that's going to be R'(L) in parallel with little rp. So we've got 91K in parallel with 80K, and that gives us about 42.6 k ohms. Now let's find our voltage gains. For stage 1, we have AV1 equals negative GM times R'(P). That is negative 1.25 millimos times 42.6K, and that works out to be about negative 53. So we've got a fair amount of gain from this first stage. AV2 is negative GM times R prime P divided by 1 plus GM times R prime K. And remember, no bypass, so R prime K is 1.5 K ohms. And this is going to give us a numerator the same as our previous gain, negative 53, divided by, it works out to be about 2.9. So our voltage gain for stage 2 is negative 18.3. So it's significantly higher gain this time with the 12AX7, and that's what we expected. That's why we made that substitution. Now, I'm going to move on over to the next page and give you a nice version of all this stuff in a second, but I have to say it really was nice switching to the 12AX7 here, because the scaling is different and it really gives us a little bit more room to work on the curves, which is nice. But anyway, here is all of that stuff consolidated into one decent graphical representation. So I'll give you a second to take a look at this, and then we'll get to work on the AC load lines. Okay, here are the AC load lines, and to save some time, I did all the work ahead of time here and set it up nicely. So basically, there's not really any significant difference between the two stages. We're assuming we've got the same R prime L value, and the only difference is we're adding in a little R prime K for the second stage of 1.5 K ohms, and it really doesn't affect the AC load line that much. So the two load lines are shown here superimposed on top of each other in yellow and red. And let's do a little comparison of these load lines with the load lines we got for the original version using the 12AU7. Okay, here's all the load lines, and for the original version, again, there wasn't too much difference between the AC load lines. We get a little bit more output voltage swing in the positive direction for the second stage. But the main thing to notice here between the original version and our modified version is that we've got a very asymmetrical Q point location on the AC load line over here. We've got a VO max of 116 volts for stage 1, 139 volts for stage 2. The minimum or negative clipping level is about the same for both, but when we move to the 12AX7 version, we get almost symmetrical clipping, which could be considered to be a positive improvement, and we definitely get more voltage gain. But you know, this is a significant change, and it's not bad. Actually, it's pretty good. This doesn't always happen when you swap tubes, but in this case, it seems to work out pretty well. And remember, we don't usually get hard clipping when we move the Q point over past our VGK equals 0 volt curve to the left here towards saturation. That's just the point where we're going to get significant grid current flowing if we do move the Q point past this curve. And we normally don't want to do that, but you know, it is possible to swing the Q point further to the left, so we could get more negative output headroom here. But anyway, that wraps it up for today's video. We're going to continue with the analysis of maybe a few more amplifiers that are out there, and I might slow down on video production a little bit here since we're getting towards Christmas, and I'm not going to leave you with a homework problem today. I don't want to give you homework over Christmas vacation, so we're just going to let it go at this today, and I'll see you guys next time around.